Welcome to Unit 7 Day 8, Part 2. In the last video we talked about the basic setup for an exponential word problem, and we talked about the story that we tell that's represented by that formula, where f of x is an end amount after starting with an amount a, changing it by a rate r, and waiting a certain amount of time t. In the problems that we'll do in this video, we still have that basic setup, but we use slightly different language to describe how something is changing. This is language that you should be very familiar with because it's all around the world around you. This is the language of percents. Sometimes we describe change by saying how much more or less there will be instead of just how it will change. Consider this example. If I say next year Nike will produce 20% more shoes than they did this year, you probably have an intuitive understanding of what that means. That means if this year, which is 2014, they produce, 100 shoes, let's say, next year they're going to produce more than 100. And to get that number, I would have to add a certain amount to 100. The amount that I add comes from multiplying 20% times 100. And of course, we change the percent to a decimal. So if you don't know how to do that, make sure that you review this real quick. You have a percent. The percent symbol has two little dots, and those dots represent decimal places that are misaligned. So if you look at where the actual decimal place is in 20 at the end, we're going to move it 2 times. And the way I remember this is we move it away from the percent symbol. It's like it's running away. So if this decimal runs away 2 times, 1, 2, 20% is actually 0.2. So when you multiply 0.2 times 100, 0.2 times 100 is actually the number 20. And this doesn't mean that in 2015 I'm only going to have 20 shoes. I'm going to add 20 to what I already had, which means I will have 120. If you repeat this process to figure out what they would have the year after next, you'll end up with a little table that looks kind of like mine. And in this table, you'll notice something that's a little surprising, which is this table is not linear growth. We're not just adding the same amount each year. It actually grows by more and more each year. It turns out that this is an exponential growth pattern. But to find the multiplier, which I've shown you right here to be 1.2, it's not entirely obvious when you first look at this why 1.2 is the right thing to multiply by. So let me run you through a couple reminders. We're using this formula, f of x equals a times r to the x. What I would like you to do is think of the percent that's given to you in the problem as a total amount. So when we say they'll produce 20% more shoes, what we really think is that there will be a total of 120% at the end, or the next year. This total amount is your change factor. Of course, we convert it to a decimal by running the decimal place 2 times away from the percent symbol, in other words, 2 times to the left. So let's look at some examples. If you invest $300 in a bank account, earning 4.8% interest, how much money will you have after 20 years? Clearly, 300 is your starting amount. Now, 4.8% interest is telling me something about how it changes, but it doesn't mean that 4.8 is r itself. You have to do this extra calculation. When they say the bank is going to give you interest, they mean that that's an extra amount of money that they will add to your account after the year. So the total amount that you'll have is 104.8%. To convert that to a decimal, I move it 2 times to the left, which means my change factor r is 1.048. If this is still confusing to you, I want you to pause the video right now, rewind 30 seconds, and listen to it again. If this makes sense, so should the rest. I plug into my formula, it's the same as last time, and then all I'm doing is evaluating. Notice that this is the easy kind of problem because I'm looking for the total. If I were looking for the time instead, this would be much more challenging. For example, look at number 2. A $30 pair of jeans is on sale. Each day of the sale, the price drops 15%. You only want to spend $15, so how long should you wait before you go to the store to buy them? $30 is the starting amount. And then dropping 15% tells me about the change, but it doesn't mean that 15% itself is r. And in fact, the calculation this time is one step more complicated because you have to be paying attention to the language. Dropping 15% means that the total percent after a day is going to be 85%. If you were tempted to say 115, stop and reread the first sentence of this problem. Okay, dropping 15% means you'll have 85. I got that by subtracting 100 minus 15. You always start with 100. You either add or subtract based on the situation. Once you have 85%, you can convert it to a decimal, and that becomes your change factor R. For those of you who already know about compound interest, I'll just make a note here that in this language, since compound interest is not mentioned directly, all of the percents are being added or subtracted from 100. If we were doing a compound interest problem, I would be using a different formula and I would not be adding or subtracting from 100. The rest of the work should be self-explanatory at this point. We're looking for the time, which is the exponent, which means I had to use a logarithm. There is no way to do this logarithm in your head, so I used my calculator to put a change of base formula in and ended up with 4.33. When I interpret this in a sentence, your sentence should make sense. It doesn't make sense to tell someone to wait 4.33 days. It makes sense to say to go back on the 5th day. That's what your sentence should say. Here are some problems for you to consider. If you flip the page, this is your first example. If you aren't done working this out, pause the video. When you press play, I'll show you the answer. Example 2. And here's the answer. Problem number 3. And your answer. Problem number 4. And your answer. Problem number 5. And your answer. And problem number 6. And your answer.